Alright, hi, it's Griffin, and we are going to be working on implementing PID. So in the last lesson you learned about what PID is, how it's used. Now the step is to actually use it in your code. Specifically here, we're going to set up PID on the shooter. So PID is a type of configuration, so we're going to go and edit our shooter configurations to add PID. Going to our shooter subsystem, we have our configurator applying our constant configs. And to add in our PID constants, we're going to edit these configs. So inside of our constants file, right where we set up our TalentFX configuration, we're no longer going to create a blank, newly constructed TalentFX configuration. We're going to add a clause to it. And the way you do that, just like we did with our current limits, is with a .with method. So I'm going to go into the next line and start typing right here. We're going to add a .with slot 0. Now you might be asking, slot 0, that's not PID, but actually it holds your PID constants. TalentFX motors have multiple slots where they can store different sets of PID constants that you can use at different times. Slot 0 is just the default slot that it pulls these PID constants from. So now we need to actually create a slot 0 object. We can do that above right here. We're going to create a public static final slot 0 configs. I'm going to call it PID underscore configs equals new slot 0 configs. And then right here on this slot 0 configs, we're going to use .with. So on the slot 0 configs, we can use .with, and you'll see, whoa, that's a lot of different constants that you can use. We're only going to be focusing on .with KP, .with KI, and .with KD. You'll see right here we have an error because we didn't actually put in our constant. So let's just say we'll put in 2 for the P, 0.00, 1 for the I, and for the D we're going to put 0.05. Now these are just random numbers that I came up with out of the blue. They don't have any significance. On your real robot, you would have tuned these based on how you see your robot function in the real world. So with the demonstration numbers aside, now we can apply this slot 0 config to our TalentFX configuration. So right here we can just type in PID configs. Great. Now we have our PID configs stored on our motor's configuration. And if you recall, we don't have to add any extra code here because we're already applying that same configuration object. Next up, we need an actual way of telling the shooter how to move based on PID. A percent out is just a percentage of voltage, so we want to use some sort of real-world value as a target for these shooter motors to reach. And typically, you'll see with a flywheel shooter, you want them to reach a certain RPM, or number of revolutions per minute. This is considered the velocity of the motor. That means that we're going to want to control the motor through velocity control. The way you do this is by creating a control object. We're going to create a private velocity voltage object. This is the type of control that we're going to use. We're going to call it velocity request, because this is going to hold the velocity that we are requesting. Now for some good Java practice, let's just instantiate it down here. Velocity request equals new velocity voltage. And by default, we're going to set it to have a value of 0 for the velocity. You'll see that this method also has some values of its own to update. If you want, you can change the slot. Like we said, there's different PID slots that you can hold, and there's some other stuff that we won't be working with right now. Now, a question you might have is, what does this voltage mean? We know velocity is going to be RPM, the way that we're controlling it, but what does voltage mean? This just means the way that we're going to try and tell the motor to get to a specific velocity. We're going to do it by feeding voltage to the motor. Now, some other options are duty cycle, which is feeding a certain percentage of the voltage to get the motor up to speed, but this can be a little less accurate. There's another way that you can use a torque control, but this requires a Phoenix Pro license on your motor, which we don't want to bother with right now. So that's why we're using voltage. Another thing that's important to recognize is hovering over this and reading the docs. You'll notice that this value of velocity represents the velocity to drive toward in rotations per second, not rotations per minute. So that's initially a little bit confusing. So if you plugged an RPM value into here, like let's say 1000 RPM, it's going to actually read that as 1000 rotations per second, which is a lot. So we're going to need to do some converting later in our code. Next up, right alongside our run shooter method, we're going to add a new setting method. We're going to call it public void run shooter velocity. And as an argument, we're going to pass in a double RPM value. Now we're still going to have to set something to the shooter primary motor, but we're not using just .set because remember that's for a percentage. We're going to use .set control, and the control that we're going to set is this velocity request object. You'll see that the code auto-corrected for me. So we are taking this object that we created right here and applying it as the motor's type of control. Now if we just left it there, you'll see we're never actually using this RPM value. This is just going to tell the motor to go to a velocity of 0 forever, which isn't very useful to us. What we want is to apply this RPM to this request. You can do that right here with .with velocity. Now remember, the CTRE API works natively in rotations per second, so we can't just apply an RPM. We need to multiply it by a conversion factor. Now let's think. For every 1 minute, there's 60 seconds. So that means that for every 1 rotation per minute, there's a 60th of a rotation per second. That means that our conversion factor is going to be 1 over 60. For example, if we plugged in a RPM of 600, we'd want to convert that to a rotations per second of 10. Because if there's 10 rotations per second times 60 seconds in a minute, you get back to 600 RPM. So the way we're going to do this is by just simply multiplying this by 1 over 60. Now you could do it something like this, but it's better practice to use a constant. So we're going to go into constants.java again, and under our shooter constants, we're going to add a new constant, and we're going to call this public static final RPM to RPS. And I forgot, this is going to be a double. Public static final double RPM to RPS. And we're just going to make this equal to 1 over 60.0. Remember that 0.0, so then it doesn't do Java integer division. Now in our shooter subsystem, we can just multiply RPM by shooter constants dot RPM to RPS. So now we're taking our RPM, multiplying it by 1 over 60, and that results in our rotations per second velocity. Great. Now next up, you might want a way to access the shooter's current velocity. Because remember, just because we told it right here to go to this RPM doesn't mean it's going to actually be there. For example, if we tell the shooter motor that it needs to be at 5,000 RPM, it's not going to instantly be at 5,000 RPM. In the real world, it's going to take some time to spin up. That's why we have PID to help tell it how to spin up. So often in your code, it's valuable to get data on what your shooter is currently in the real world spinning at. Sometimes it can be used to compare to what you want it to be spinning at. So in our printing section right here, I'm going to add a public double get RPM, and we're going to return shooter primary dot get velocity. Now we have an error. Unlike dot get, which returns -1 or 1 for a percent out, get velocity actually returns a status signal object, which contains some extra information. The way to actually get the velocity from this is to use .get value as double. Now next up, remember, this works in rotations per second, so we're going to need to convert this to rotations per minute. So if this is 1 rotation per second, then in a minute, there's going to be 60 rotations. So here we actually want to multiply by 60. Now a way that I like to do this is by creating another constant, public static final double RPS to RPM, and this is going to equal the opposite of RPM to RPS. So you see, now these two are kind of linked, so if you change one, the other changes. This can help keep track and make sure that if you change a constant here, you don't forget to rechange it right here. So once you have the inverse conversion set up right here like this, we can multiply shooter primary dot get velocity dot get value as double by shooter constants dot RPS to RPM. Now we'll be getting an RPM value. Let's go ahead and print it out in our periodic. We're going to call it shooter RPM, and we're going to use get RPM. Now that we've configured the subsystem to be able to accept a velocity in RPM, we need a command that will allow us to command the subsystem to move at that RPM upon certain button presses. Let's do that by creating a new command, and we're going to call it shoot 1000 RPM command. So as the name suggests, this command is going to set the shooter to run at 1000 RPM. Now this is going to be the same steps as creating any other command. We're going to store our private shooter subsystem named shooter subsystem. Import it right here. We're going to receive our one shooter subsystem object in the constructor. Remember, that same one that we pass around through every single file that needs it. We're going to add it as a requirement. And above here, we're going to set our local shooter subsystem pointer to the one that we passed in. Remember, this is all the same object that's being passed around. And another thing we're going to do is create a final double called RPM that we're going to set to 1000 that we can then pass into our method. Now, where do we call the method? I like to set the request in execute so that I guarantee that it's updating consistently. So in execute, let's do shooter subsystem dot run shooter velocity with our RPM value. That's a final up here. It's going to pass in 1000 as our RPM value. And then finally, don't forget in end, when this command is over, that we want to set the shooter subsystem to stop. So in our robot container, let's actually add a new button to be used with this new command. We're going to go on m_driver controller dot, and remember that we can either use a ID'd button like we did in this example right here with button 2 specifically, or because this is a command Xbox controller and I have a official Xbox controller, we can trust these trigger button assignments that it has preset in its code. I'm actually going to use Y. And just as a double check, I'm going into my driver console and I'm going to check pressing Y is button 1, 2, 3, 4, which we have not used yet. Great. We're going to make it another toggle on true for a new shoot 1000 RPM command, passing in our shooter subsystem, as always. Let's simulate all this. So going into our sim, we see that we have a new shuffleboard printout for shooter RPM that we set up. So let's see what happens when I press my Y button. Pressing in 3, 2, 1. Looks like nothing happened. Let's troubleshoot and see if this is an issue with sim or not. Remember, you can use your sim GUI to confirm. Let's take a look at motor 6, which is, if we check back in our code, our shooter primary, and we see that it is running with the duty cycle. So yet again, we see one of the glitches with sim. Pressing the button, sometimes this %out's working, sometimes it doesn't. You can always check here to confirm. But one thing we see is, hey, the shooter RPM reads 0. Now, we see that there's a %out, so the shooter must be doing something. It's getting some sort of voltage applied. So why do we have no RPM? Well, this is another limitation of the simulator. Because determining RPM is dependent on having a sensor physically on the motor that can count the amount that's rotating, and of course, you don't have a motor physically plugged into your computer. It's just all simulated. We aren't able to get this info from the simple WPI sim. That's why we don't have a value right here. So we see yet again one of the shortfallings of sim, but overall, because we see that upon toggling the command, we get a %out, we know we're commanding the motor. It'd be up to you to see in person if your PID gains made it function as you'd expect. That's configuring a Talon Effects motor to use PID constants and velocity control. Next up, we got another part of the motor tuning process.